Greetings everybody. This is the second video for part 4 of the Chapter 7 lecture notes. And remember, we covered Hooke's Law. We did the lab on Hooke's Law, or we're in the process of doing the lab on Hooke's Law. And remember, Hooke's Law gives the equation for the force that a spring exerts on an object, assuming that object is obviously attached to a spring. And Hooke's Law gives us the force on the object when the spring is either stretched or compressed by a distance of x. So F is equal to minus kx. Remember, the minus sign means in the language of physics that it is what's called a restoring force. It always acts so as to pull the object towards the equilibrium position. And again, in this figure, part B is when the spring is at its equilibrium position, i.e. its natural length, meaning in panel B, the spring is neither stretched nor compressed. In part A, the string is stretched a distance of x in the positive x direction, and the restoring force, the spring force, is directed in the negative x direction because you're pulling in part A. The mass is being pulled away from the equilibrium position, indicated by the dotted line, i.e. the position of the spring when it is in its equilibrium or natural position, meaning it is neither stretched nor compressed. And then all the distance x is measured relative to the equilibrium position. So panel A, mass is pulled in the positive x direction, spring force acts in the negative x. Hence, F is minus kx. Panel C, the object is compressed in the negative x direction. The spring is compressed in the negative x direction. When you release the mass, the spring force acts in the positive x direction. But in other words, the spring force always acts towards the equilibrium position. Well, when you stretch or compress a spring a distance x, always by that we mean relative to the equilibrium position. Again, panel B is the equilibrium position. So when you stretch or compress the spring a distance x, the energy stored in the spring, the PE spring, is equal to 1/2 kx squared. Remember, k is the spring constant. Every spring has its unique k value. The larger the k value, the stiffer, i.e. the less flexible the spring is. The MKS unit of k is a Newton per meter. And so Hooke's Law, the restoring force, F is equal to minus kx. Don't let the minus sign throw you. It just means, as in panels A and C, that, if you, again, in panel A, if you stretch, the mass is on the spring. If you stretch it in the positive x direction, spring force acts in the negative x direction. Panel C, you compress the mass in the negative x direction, spring force will act in the positive x direction. They're always opposites. See? So hence the minus sign. And again, B is the equilibrium position of the spring. Well, you also store energy in the spring. In joules, that spring potential energy is 1/2 kx squared. Now, the spring force is what's called a conservative force, meaning that in the language of physics, not conservative politically, but conservative means that for, so Hooke's Law, F is equal to minus kx. That's a conservative force. mg, the weight of an object, mg, gravity, is a conservative force. Well, what does it mean? Well, for a conservative force, what makes it conservative is that the work done by the conservative force on an object moving between any 2 points, call them A and B, the work done is independent of the path. So in other words, that's part one. So in other words, suppose I'm moving an object from A to B. I could take the direct purple line, A to B, or I could take this red meandering path and go from A to B. Well, if the force that's moving the object from A to B, if that force is conservative, it means that the work done by that force on the object, the work done will be the same no matter which path you take, whether I go A to B along the purple path or A to B along the meandering red path, the work done will be the same. That means it's a conservative force. And also, the work done by a conservative force moving an object through a closed path is zero, meaning you start and end at the same point. So here, suppose I go start at A, take this meandering path, but then end at A. That's what we mean by a closed path, that you start and end at the same point. The work done will be zero. And we call that conservative forces are also called path independent forces. Well, the two most important are the weight and the spring force. The mg and kx are conservative forces. Friction, which we'll prove in another lecture, friction is a non-conservative force. The work done will be different depending upon which path you take. But conservative force, again, very simple. If the force moving the object from A to B is conservative, the work done taking the purple path and the work done taking the red path, even though those paths are completely different, the work done will be the same. Well, this leads to something very important concept of physics, a very important concept of physics called conservation of energy, which I abbreviate COE, conservation of energy. When we say take the energy approach, we're going to mean either the work energy theorem or conservation of energy, not Newton's second law. Well, it states that in the absence of any non-conservative forces, remember, in the absence, and for our intents and purposes, the non-conservative force that we're going to worry about is friction. Friction is non-conservative, but we don't need to worry about that right now. So we're assuming that there's no friction. Conservation of energy states that the initial kinetic energy of the system, typically the system is one or more objects, the initial kinetic energy of the system, so the initial kinetic energy of the system plus the initial potential energy of the system is equal to the final kinetic energy of the system plus the final potential energy of the system. And again, don't let system confuse you. Typically the system will be one or more objects. And typically if there are two or more objects, they're going to be connected typically via a string. And then, that goes over a frictionless pulley. But so we have KE initial plus PE initial equals KE final plus PE final. What's KE? Remember, KE is equal to 1/2 mv squared. Well, remember now, notice the arrows. The potential energy, the initial, and or the final. The initial potential energy could be some combination of gravitational and spring potential energy. Remember, those are the two that we're concentrating on. The two types of potential energy that we're most interested in are spring and gravitational. So the PE initial and PE final, they could be mgh and or 1/2 kx squared, because we are dealing now with two types of potential energy, gravitational and spring. Well, spring is very simple. Potential energy is 1/2 kx squared. What is k? The spring constant. What is x? The distance that the spring is stretched or compressed. In MKS units, k is a Newton per meter and x is in meters. But PE spring, 1/2 kx squared. PE gravitational, mgh, where h is the height relative to the reference point. So let's look at one example. Here in this figure, we have a ball of mass m dropped from rest from a height h above the ground, as shown in the figure. So it's dropped from rest at a height of h above the ground. And I wanted an expression for this, and we always neglect air resistance. Well, not always, but in this case I'm telling you, neglect air resistance. Air resistance is a type of friction, which again, we're going to worry about friction when the time comes in the next lecture. So right now, no friction. Well, I want an expression for the ball when it's at a height of y above the ground. It's released from rest at a height of h. When it is at a height of y above the ground, I want an expression for the final speed. Now remember, this is gravitational potential energy. The height of the ball is changing. It starts off at a height of h above the ground. I want an expression for VF when it's at a height of y above the ground. Well, let me go ahead and let's do this problem a couple of times. Let me choose the ground as the reference point. We're saying that what we're saying is this. Let me pause it for a second. Okay, so what we're doing is we're going to solve example 1 3 times. Part A, when we choose the ground as your reference point, indicated here by the green dotted line, meaning, remember, reference point, that's the point that you choose where we say PE is 0. So we're saying that in part A, the PE is 0 when the object is, at the ground. Part B, we're going to choose Y as our reference point, the blue. So part B, we're going to solve it choosing Y as our reference point, meaning when the object is here at the point Y, its PE is 0. And then part C, we're going to work it with the initial starting point H as the reference point. So we're doing it, so we're choosing the green, then the blue, then the purple. So we're just solving, and we should get the same answer each time because the reference point is simply a mathematical tool. We choose it so as to make the math easier. And again, part A is probably the easiest. Choose the lowest height as the reference point. Let's go ahead and work this problem. So let's do part A. And conservation of energy means we always start off with this equation right here. KE initial plus PE initial equals KE final plus PE final. The PE could be MGH and or 1/2 kx squared. Well, obviously in example 1, it's just MGH. Okay, but I'm going to start off, here's the equation. KE initial plus PE initial equals KE final plus PE final. Well, what is the KE initial? It's 0. So that's why from line 1 to line 2, why did I drop the KE initial term? Because it's 0. Because the mass is dropped from rest. So now I have PE initial equals KE final plus PE final. What I'm saying is that the initial potential energy it has at H, that is equal to, remember, once you drop it, it begins to move. It begins to acquire a speed V. So right here at Y, when we're calling the speed V final, the mass now has kinetic energy because it's moving, 1/2 mv final squared, and it also has a potential energy because its height has changed. Okay, so it has, so step 1, KE initial plus PE initial equals KE final plus PE final. KE initial 0, so I have PE initial equals KE final plus PE final. Well, remember, part A, the ground is the reference point. So the initial potential energy is MGH because initially it is at a height of H above the reference point. Remember, part A, we're using the green as our reference point. So its potential energy is positive because it starts off above the reference point. So MGH equals, well, this is never going to change. The final kinetic energy is always 1/2 mv final squared. Now the final potential energy right here, it is now at a height of y above the reference point. Still positive. Remember, in part A, the ball starts off above the reference point, MGH. Here, when we want to determine V final, it's at a height of y above the reference point. So the final potential energy is MGY. Well, algebraically, it's not complicated to solve for VF. The masses cancel. Take the GY term to the other side. It becomes negative. You've got the pull out the G, then you have H minus Y in parentheses, multiply by 2, then take the square root. But you get VF as root 2G parentheses H minus Y. And remember, in part A, we're choosing the ground as the reference point. So PE initial is MGH. It's at a height of H above the reference point. PE final is MGY. When we want V final, the ball is at a distance of Y above the reference point. Then algebraically solve for VF. And you get root 2g parentheses h minus y. Now let's do part B, choosing y as the reference point, and then part C, choosing h, the purple, as the reference point. Let me save this video and do B and C in another video.